All right, this is Physics 1C for October 29th, and we're going to do a quick review of what we talked about last time. So last time we talked about this thing called Faraday's Law, and Faraday's Law is the idea that if you have a changing magnetic flux through a coil, it produces an EMF, and this is the idea behind how power is generated. You move a magnet near a coil, it produces electricity. So as long as you can make the magnet move in some way, then you can generate electricity. And you can do that by water falling from a dam, or you can do it by heating up, fossil fuels and then heating up water and using steam to turn turbines and stuff like that. But what Faraday's law states is that the EMF that gets introduced, or that gets induced in the coil, ends up being equal to, you get a negative sign, the number of the turns in the coil, and then the time derivative of the magnetic flux through the coil. So we're going to use that to solve this problem right here, which is a problem that kind of addresses a common mistake sometimes people make, and a question that I get a lot about how to solve these problems. So let's read this. I'll make the problem a little bigger. This is the picture for it. I think it's a pretty nice picture. This one doesn't come from your book. It comes from a different textbook, but all right. So here we go. Okay, it says an aluminum ring with a radius of 5 centimeters and a resistance of 3 times 10 to the negative 4 ohms is placed around one end of a long air core solenoid. So we've got this solenoid right here. The solenoid, just to remind you, is just the fact that you've got this core and then a bunch of coils wrapped around it. That's what makes it a solenoid. It's just, literally, the word solenoid, you might as well just call it coil. Anyway, all right, so it has 1,000 turns per meter. Now that's the turns here in the solenoid itself, and it's the turns per meter too. The solenoid has a radius R2, which is the smaller radius here, of 3 centimeters, and we want to assume, this jumps right into it, but we want to assume that the axial component of the field produced by the solenoid is 1/2 as strong over the area of the end of the solenoid as the center of the solenoid. We'll talk about what that means in a second. And it says, also assume the solenoid produces negligible field outside of its cross-sectional area. The current in the solenoid is increasing at a rate of 270 amps per second. We need to find the induced current in the ring. And at the center of the ring, what are the magnitude and the direction of the magnetic field produced by the induced current in the ring? Kind of a mouthful. It's quite a long problem. Does anyone have any questions about what's happening here? So coil has current flowing through it. That current changes. That changing current is going to produce a changing magnetic field, and that changing magnetic field is going to induce electric current in the golden ring right here, and that's what we want to calculate, is what is the current going to be flowing in this ring right here. That's what we're looking for here. All right, so where do we get started? What do you think? How should I start this? What should we figure out first? I want to find the direction of the magnetic field. The magnetic field that's produced by the solenoid or the induced magnetic field? do we have to integrate? Sorry, where are the two magnetic fields coming from? Okay, so is there going to be a magnetic field that's produced by the solenoid? The first question I would ask. Yeah, okay. So there's a magnetic field that's produced by the solenoid. I'll call it B solenoid. We don't know what that is. Okay, Ash's question is, so to be clear, is the solenoid the magnetic which we're turning to make a current in the ring? The solenoid is going to produce a magnetic field, right? Because if you have a piece of wire wrapped around a coil like this, it's going to produce a magnetic field. I would say in this case, it's going to produce a magnetic field that's going to point this way. You can use your right-hand rule to kind of verify that's true. That based on the direction the current is flowing, like the current's going this way, it's going around in that direction. So if you kind of wrap your fingers as if you were like gripping this tube with your right hand, so that your fingers would be pointing this way, then your thumb would basically point that way. Right? Your hand would be like this. It's a really crude hand, but hopefully you get the idea. That's the direction of the magnetic field. Now, just having a magnetic field alone, though, isn't enough to induce a current here and a current in the other ring. And to answer your question, we're not.
Class right now. What are you talking about?
Uh-oh, Faison, you might want to.
Sorry. Oh my God. Sorry.
You're fine.
Sorry.
It's okay. All right. So, to answer your question, Ash, there's no magnetic field that we're turning here, but this magnetic field here is changing in time. And the reason I know that is because it says that the current in the solenoid is changing at this rate right here. So you could say something like, you could either say that the time rate of change of the current is positive 270 amps per second. Or you could call this delta I over delta T, however you want to do it. It's just the rate of change of the current, and it's a constant. The magnetic field is produced by the current in the coil. Yep, in the silver-looking coil here, there is a magnetic field that's produced because of that. Yep. So the thing we're going to need here then is this the formula that we derived before for the magnetic field of a solenoid from the previous chapter. And that's a pretty simple, we'll call this just B sol. You take mu naught, you multiply by the number of turns per meter. That's what we have right here. And then you multiply by the current flowing in the solenoid. Now in this problem, at any moment in time, we don't actually know what the current is. We could say something like it starts at 0 or something, and if there's no current, you get no magnetic field. But there is going to be a magnetic field in the solenoid produced like this. And we can't really calculate it because we don't know what I is. All we know is the rate at which I is changing. But they don't ask us to calculate that, right? They say, what is the induced current in the ring? So we're looking for the current that's induced in this ring right here. So this is where we want to invoke Faraday's law. Faraday's law says that the induced EMF in the ring, this is going to be the gold ring that I'm talking about here, that's around the end, should be equal to negative number of turns in the ring times the time rate of change of the magnetic flux through the ring. So if this current flowing through the solenoid was constant, the derivative of the flux would be 0. But because the solenoid has a changing current with respect to time, you're definitely going to get a change in flux as well. So let's expand this out here. It tells us that we know what the resistance of the coil is, but the number of turns, I'll just write this over, the number of turns in our ring is just 1. There's only one ring, basically. So we can make that 1. So it'll be negative 1 times the derivative of flux. And flux is BA cosine theta. Now we need to think about what this is. There was a question a second ago from Anna, do we need to integrate? So we can figure out in a second if we need to integrate. So one thing I would say now is that I think this problem is a little bit easier to understand if we picture what's happening from this perspective. Like if we look at the, like basically from the left edge. So I'm saying that based on the direction the current in the solenoid's flowing, that the magnetic field points to the right. And from the left end then, what we can say is that we have this this golden ring. And then inside of that ring, we have, let's try to use like a silver color or something like that. We have this, this solenoid, which is made up of basically several turns of wire that go around and around. And looking from the left end, if the magnetic field is pointing to the right in this picture, then the magnetic field inside of here needs to basically point this way. So you've got the outer ring, you've got your solenoid, and then that's the magnetic field of the solenoid inside of it right there. And then we could label a couple other things here, although I might need to make this bigger to allow that to happen. So I don't know how much I can actually write inside of there. So the solenoid itself has this inner radius that's called R2, right? So I'll just like draw a line right there and say that that's R2. And then the other one has a radius. It's R1. No, that does matter. That's part of the question. So your question is, would the current flow counterclockwise in the ring from this view? You're not sure if that matters. So the current in the solenoid here is one thing, and if you look at the way that the windings are wrapped, the current's coming out from the left side here, which means that it goes this way. So I believe on our picture here, that current would be flowing like this way and then like this way. That would be the direction of our current here. That's also consistent with the direction of that magnetic field that's inside of it, those little X's there. So that would be the current flowing through the solenoid. Okay, so now this is the main reason why I picked this problem. So now we have to think about, let's do a couple things. First of all, can we figure out, based on the information now, what the direction of the induced current in the golden ring is going to be? What's the direction of the induced current in the golden ring going to be? This is where we have to use Linz's law, which says that the direction of the current is, yeah, counterclockwise. And how did you get that, Ash? Why is that? Linz's law tells us that, yeah, that's a really simple way to put it. It has to basically be opposite of the current running through the solenoid here. It's a very good way of putting it. So if the solenoid goes that way, the current out here has to go this way. So this is going to be the current in the ring. So that's part of the direction to the answer for our question. So now the rule for finding the current in the ring, because it's an induced current, is you have to use Linz's law. And Linz's law says the flux through the golden ring, is it increasing or decreasing? The flux, the magnetic flux through this golden ring, it's increasing. And so that tells us that the induced current has to be in such a way that opposes that change, which basically means it needs to be opposite of the current that's inducing it, so to speak, right? It's the change in this inner current that produces a magnetic field that changes the flux through the outer ring. Therefore, you need to have a induced current opposite that direction, basically. Okay. So now what about this piece here? It says we need to take the time derivative of the magnetic field, and I'll just say that this is going to be the magnetic field of the solenoid right here, multiplied by an area, and then multiplied by the cosine of an angle. So let's fill in the details here. So this induced EMF, of these different things here, the first thing to talk about is what is the area. So what do you think? Should we be using the area of the outer area here, like pi r1 squared? Or should we be using the inner area, pi r2 squared, for the area that shows up inside of here? Okay, r2. Why do you say r2? That's correct. That is the right answer. One of the things that was said, yeah, the magnetic field is combined to R2. That's that. So all the flux is in this region here, basically. That's what that means. There is no flux out here because magnetic field out here is 0. So all the flux is in here, which means that area is going to be pi r2 squared. I'm also going to say that the direction between the area vector and the magnetic field vector, we're going to take it to be basically, we're going to make theta equal to 0. You could choose 180 or 0 really here, and that would kind of change how you do this, but it's not super meaningful. So we're just going to choose theta equal to 0, and so we'll end up getting negative. The magnetic field of the solenoid, we'll put in the area we can pull out, and we said that that area was going to be equal to pi times r2 squared, okay? The area for our fluxure, and I'll just write that over here in case anybody missed that as I was talking. So pi r2 squared is the area we want here, because the magnetic field's confined here, as Ash was saying. Why is theta 0 again? Yeah. The distance between the magnetic field to the area vector. So in this case, we could pick the area vector to point into the page. Okay. Not 90, because the area vector is like in this way, and the magnetic field's in the same direction. So we'll say it's 0. The one thing, I don't want to confuse you too much, but this is kind of an arbitrary choice. Like, there's a reason to point it in certain ways, but in this case, it's not going to be super important. Okay, so what's left in here is the time derivative of the magnetic field of the solenoid. So let's just leave the derivative part there, and let's plug in what we have for the magnetic field of the solenoid. But I'm going to mention one other thing here. This isn't that important, but in this problem, it mentions, assume that the axial component of the field, axial just means pointing along the axis of the column, the solenoid, produced by the solenoid is 1/2 as strong over the area. So that means, really, this is the expression, this right here is the expression for the magnetic field of the solenoid at the dead center of it. That's the place where it's the strongest. So what it's saying is, on average, that's going to get smeared out, and it's going to be about 1/2 of that over the end, okay? And it's just a piece of this problem that we're going to use. So with that 1/2 thrown in front of it, our magnetic field of the solenoid in here is going to be 1/2 times the magnetic constant times the number of turns per unit meter, and then times I. And again, we don't know what I is, but the good thing here now is that 1/2 mu naught and little n, those are all constants. I'll write over here what little n is. N was 1,000 turns per meter, so I'm just going to call it per meter. Okay, so we plug everything in. Negative pi r squared, r2 squared. There's a 1/2, there's a mu naught, and there's a little n, and what's left is di dt. Right. And now the goal here was to find what is the induced current in the ring. So in order to get the current, we need to say that the induced current is going to be equal to the induced EMF in the golden ring divided by big R. So we get that the induced current in our ring is going to be E over R. So we'll end up basically dividing this whole thing by R. And at this point, I'm just going to plug everything in. So we have negative pi r2 squared. Whoops, I was going to actually plug things in. All right. Now, what was r2? I think it was 3 centimeters, right? Yeah, r2 is 3 centimeters. So 0.03. Dividing by 2 times mu naught is 4 pi times 10 to the negative 7. I think this is... Oh, I can't remember now. I usually remember this one. Is it Tesla meter per amp, or is it Tesla over amp meters? I'll have to look that one up in a second. Maybe you can check the units on mu naught. If someone could do that, that would be really helpful. And then we multiply this by 1,000 meter inverse. That was little n. We're running out of room here. And then times di dt, which was 270 amps per second. Oh, and then we got to divide by R. So divided by R, which was given right here, 3 times 10 to the negative 4 ohms. Okay, thank you, Anna. So I guess getting some feedback from George. So this is divided by George, can you mute your mic? I can mute it for you. Okay. This is divided by the resistance, which now I forgot what it was. I think it was 3e minus 4. Yeah. So 3 times 10 to the minus 4 ohms. That 3 looks weird. That 4s always look weird. Okay, that whole long equation there should give us the current that's induced in the ring. So if you want to calculate what that is, I can't find my phone. Can you all calculate that for me? Negative 1.6 amps. Anyone get the same thing? Anyone else also get negative 1.6? Okay, so the answer, negative 1.6 amps. All right. Not quite done. The other two. Well, let's just stop for a second because that's a lot of work we did there just to get that one answer. Does anyone have any questions? All right. So the next question is, at the center of the ring, what are the magnitude and C, the direction of the magnetic field produced by the induced current? So to get the magnitude, this is a ring of current, right? And we have an equation. This is kind of plug and chug. At this point, to find the magnetic fields at the center of the ring, we can use our equation that the magnetic field at the center is equal to mu naught times the current in the ring divided by 2 times the radius of the ring, and the radius of the ring is R1. So that's pretty easy to do. So it's 4 pi multiplied by the current whatever that gives us. It's going to be a very, very small magnetic field. Oh yeah, R1 is 5 centimeters. And to get the direction, it's kind of hard to show on here, but the direction of the magnetic field induced, the magnetic field that's induced by the induced current would be pointing out of the page. So this is going to be pointing out of the page for our answer here. What's this one equal to? Like 48 pi, whatever that is. 2 times 10 to the negative 5? Okay. And that's going to be in Teslas. And again, the out of the page is given by the right-hand rule. Current's flowing this way, so the magnetic field has to be out of the page. It's also one of the rules of Linz's law that if you have increasing flux, the magnetic field induced in the ring has to be opposite to the external field, which would be the field from the solenoid. All right, so there's a nice little Faraday's law problem that should help you with some of the things you'll see on your homework. All right, so I want to show you guys this video now as a way to break this up. This is a video that works off of Linz's law. It's a demo that we have at the school as well. So let me share the right screen. Oops. This one. could do labs in person. All right, here we go. Let me make if it's not making any sound, just let me know. I don't hear anything yet.
This short clip is a demonstration of Faraday's law of electromagnetic induction and of Lenz's law. The equipment consists of a coil of copper wire. It has a ferromagnetic core extending out from the centre of the coil. The coil is connected via a switch to a 240 volt 50 Hz AC supply. There are several aluminium rings of different thicknesses. First, a simple demonstration of Faraday's law. A light bulb is wired in series with a second coil of wire. When the current is switched on, the bulb lights up. What's the explanation of this behaviour? We know that a coil carrying a current will give rise to a magnetic field. And Faraday's law says that where there's a changing magnetic flux passing through a conducting loop or circuit, an EMF will be induced, causing a current to flow. And so the bulb lights up. In this demonstration, it might not be immediately obvious that the magnetic flux is changing. But remember, our coil is connected to an AC supply, so the current flowing through it is varying sinusoidally with a frequency of 50 Hz.
So that's something we haven't talked about yet, but yeah, like when you plug something into a wall socket, we talked about it a little bit last time, right? Because we looked at that demo, the other video. The current flowing through the coil, basically, yeah, it's like a sinusoidal current. Okay, so you automatically, this thing has a current that's changing in time constantly. Yeah, the bulb would not turn on with DC current, that's right. It's also something that you need to be clear about here, that this bar right here, it doesn't form electrical contacts with the wire that's around it. So this isn't like electricity where you just have a battery and you connect one end of the battery to the light bulb. And the other end, this is definitely induction, where the changing magnetic flux here induces a current in this other ring, just like the problem we just did. And that causes this to be able to... So the bar here, by the way, I would assume, although I'd have to look at the details of this, if they say anything, it should be some kind of iron core. It doesn't say it. But I know in the one that we do, we use an iron core because that iron core basically enhances the size of the magnetic field by orders of magnitude. Due to the magnetic constant for iron being much higher than air. He said ferromagnetic, okay. You don't have to move it to make the light bulb light up because the electricity is varying sinusoidally. That's exactly right. And the sinusoidal variation here of current, just like we saw in the previous problem, leads to a changing flux because the current produces a magnetic field. You notice also, by the way, as he moves it up and down, that the light bulb got a lot brighter as he got lower, which tells you that the induced current has to be bigger than, too. That's because the magnetic field near the core of the solenoid is bigger than the magnetic field up here. It produces a magnetic field throughout all of space. Yeah, exactly. Yeah, exactly. That's right. Okay, because at the poles, that's where the density of the flux lines are the highest, right?
And so the magnetic field that it produces also varies sinusoidally at the same frequency. Now, for a more dramatic demonstration of Faraday's law and the effects of Lenz's law. When the current is switched on, a magnetic field is produced that induces a current to flow in the aluminium ring. Like all currents, this induced current will produce a magnetic field of its own. Now, Lenz's law states that the direction of any magnetic induction effect is such as to oppose the change producing it. So the direction of this induced magnetic field must be in opposition to that from the coil.
So the question is, would this work without the bar? I don't think if the bar wasn't there, I think it just jumps a little bit. No. The bar guides it, though. That's all it's really doing, Mr. Meowers, is it's kind of guiding it upwards, right? It would kind of... my guess is that it would kind of shoot off in one direction, or it might wobble. It's a good question, though. It's something I could test if I went back to school. So.
the ring experiences a repulsive force and is launched into the air. We can easily show that the force launching the ring into the air comes from an induced current flowing in the aluminium ring. This time there is a gap in the ring. It isn't a complete circuit, and so no current flows. Now, what would you expect to happen if we repeat the experiment with the original ring, but this time we cool the ring first?
Yeah, there's no. It's like an open circuit, right? Like if you can't if there's a gap in the ring, there's no complete circuit and there's no magnetic field. Basically, there's an EMF. Where's it going? The only reason you had an opposing force before was because you induced a current in the ring. That current has a magnetic field. That magnetic field opposes the existing magnetic field, so you get repulsion. That repulsive force was only there when you had the current. If you put a gap in the ring, you can't, there's no, it's like, I'll put it this way. Remember the problem we did last time? We said that there's an induced EMF, but there's no current because the resistance is really high. So one way to think about it is that that gap introduces a huge amount of resistance to the ring, because in order for current to flow, you'd have to have a spark that would flow across the gap. Does that make sense? You'd have to have a spark that could jump through the air, and the resistance of air is very high. So that's one way to think about it. The easier way to think about it is that, dielectric breakdown. That's what that's called when you get that spark. But that's easy. The other way to think about it is just if there's a gap, you can't have current, basically. There's no way it's going to flow.
You should recall that when we cool a conductor, its resistance decreases. This means that the induced current that flows in the ring is much larger, and so the repulsive force experienced by the ring is also much larger.
That's pretty cool.
We've seen what happens when a ring is placed right on top of the coil and the supply is then switched on. What if we start with the current already flowing and then place a ring over the ferromagnetic core? The principles at work are just the same. The current induced in the ring due to Faraday's law produces a magnetic field that is in opposition to the field from the coil. The difference is that in the previous demonstration, the ring starts very close to the coil, and so the repulsive force experienced by the ring when the current is switched on is very large enough to launch it into the air. In this case, the ring hovers at an equilibrium point where the downwards force due to its mass is balanced by the upwards electromagnetic force. So what if we replace the ring with a thicker one, with a greater mass? Despite being significantly heavier, the thicker ring seems to levitate at roughly the same height as the thinner ring. The reason is once again related to the resistance of the ring. The greater cross-sectional area of the thicker ring gives...
Do you guys want to try to figure out why it is? You could probably figure it out. He kind of gave you a hint there. The thicker ring's heavier, right? Why does it hover at the same height? And keep in mind that the height it's hovering at is related to the current, I guess you might say. More area for the current to travel through. And what do y'all remember what the relationship is between you're right, Ash, you're thinking about it conceptually correctly, that there's more area there for the current to flow through. What is the bigger magnetic field? Sure, because of the larger current, absolutely. What is the biggest difference between the two of them? Their masses are obviously different, right? The bigger one is obviously bigger, right? There it is. The resistance of the ring is rho L over A. They're both made of the same material, so rho is the same. The length is the circumference, and A is the cross-sectional area. So the resistance now is going to be lower or higher? on the one on the right. The thick ring have a higher resistance, or it's lower, yeah. So even though it's like more material, so you might think, oh, more material, more resistance, the fact that it's thicker means that the cross-sectional area is bigger, which means the resistance is lower. If the resistance is lower, the current goes up, right? Given the same EMF. And they're both experiencing exactly the same EMF, remember that. Because the EMF at that point, right, is related to number of turns times the time rate of change of the magnetic flux. They're both the same size, so they're the same area. They're both experiencing the same rate of change of magnetic flux because they're both being affected by the sinusoidal, what do you call it, the power source, right? So if you had a ring with a larger radius but the same thickness, would it be lower? Okay, that's a good question. So larger radius but same thickness. What would that mean about the induced current? Sorry, we should go one step at a time. Yeah, resistance would be lower. Larger radius, I think, would have a bigger resistance, right? Because it's more material. Yeah, circumference is larger. Something tells me, though, that if the radius is larger, the magnetic field might be weaker, too, though. Right? Because if the radius is larger, and then... yeah. So if it's bigger R, which would mean lower current... yeah, I don't know. Okay, I'm going to push play here. I'm going to let this one finish. I have to step away for a second.
It's a lower resistance, and so the current induced in this ring is bigger than the induced current in the thinner ring. So the increased weight is balanced by a larger electromagnetic force due to the larger current. The explanation of the jumping and levitating rings presented here is useful as an illustration and reminder of Faraday's law and Lenz's law. It should also remind you of a couple of key facts about resistance and about magnetic fields due to current-carrying coils. Actually, the explanation given here is somewhat simplified. If you're happy with the concepts explained here, you might want to think a bit more deeply about the following. Think carefully about the nature of the magnetic field produced by an alternating current. And think very carefully about Lenz's law. The levitating ring demonstration suggests that the magnetic fields are always repulsive. Is this actually what you'd expect? And, if not, how do you explain the levitation? And if you want something else to think about, watch this final demonstration and see if you can explain the behaviour of the thin aluminium foil ring. Think carefully about the nature of the magnetic field produced by an alternating current. And think very carefully about Lenz's law. The levitating ring demonstration suggests that the magnetic fields are always repulsive. Is this actually what you'd expect? And, if not, how do you explain the levitation? And if you want something else to think about, watch this final demonstration and see if you can explain the behaviour of the thin aluminium foil ring.
Oh, whoops. I muted that whole time? I'm sorry. I forgot to turn it back on. What do you think's going on with that last part? First of all, I guess the question would be, why does the aluminum ring fall down like that? Oh, there was a question that said, is the levitation because the material is aluminum, which is diamagnetic? No, I don't think so. I think it's just because of Linz's law. There's something else going on that they're not mentioning here, but I don't want to directly mention it until we get to AC current and we talk about phase angles. Because there's, I guess I could kind of introduce it a little bit. Think about, like, so, okay. First of all, does anyone have any idea why this the smaller foil fell down? The rate of change of magnetic flux isn't high enough, so the levitating force isn't strong enough to oppose gravity. Maybe. I think it's the thickness too, Anna, right? If it's really thin, what does that mean about the induced current? It's very small, yeah. Resistance is really high, right? Yeah, exactly. Yeah. I think that's right. Now, I don't know what happens here, though. This is interesting. I mean, you're definitely getting an opposing magnetic fields at the top here, right? So you have, there's a combination, there's two different things that are now inducing current in this ring. And what I would assume is going on here is that the induced current in this is not enough to, like, lift it up. But I think if you add the induced current from the top one, I think that's enough to lift. So you're getting a kind of a sum of forces here kind of deal. There's two different forces acting on the ring now. And there's two different changing fluxes happening in this little ring. So something like that going on, probably. Maybe. And then it sticks to it, which is great. Up to a point where he pulled it up high enough and then it didn't anymore. But it also, I think he pulled it, I mean, yeah. That's really neat. I have to try this now. I have to go to the school and try this out because we have one of these things. Do you have a question? No, okay. You said the foil ring is traveling along the magnetic field that happens from the top ring. Yeah, something like that. Something like that, yeah. Or a combination of both of them. I'm gonna introduce something else to have you think about something here. This is kind of related to a problem I was gonna do, but I think it's interesting enough. So we have a situation here where we have like a solenoid, basically. And that solenoid, we said before, has this current that's running through it, but that current is changing with time, right? So literally the current as a function of time is some kind of like I max, whatever the maximum current is, multiplied by like the sine of omega t. Right? Oh, one note. I got to turn one note on. Right, okay. Thank you. Sorry. Alright. So, the magnetic field of the solenoid is given by that expression. And then the current flowing through the solenoid on the bottom is given by that expression right there, right? And in this problem, what you've got is you've got your base, and then you've got your solenoid right here, and it's got all these wires running around it right here. And you've got your core. And then we've got our ring. We'll put a ring around this. So there's our ring. So we're wrapped around that right there. So do you want to talk about the flux through this ring and what's happening to it? So let's draw a graph. We need probably this type of graph here. We need to go a decent amount. And on this graph, what we're going to do is apparently not be able to move it. We'll go this way here. So on this graph, what we're going to do is we're going to plot two things. We're going to plot the current flowing through the solenoid, and we're going to plot the induced current in the ring with two different colors. So first, I'm going to plot this. This is the current in the solenoid, as referenced by the kind of gray. This is the solenoid here, okay? That's a simple curve to plot, right? We just need to have a couple markings here to kind of divide it up, and then have a maximum, a minimum, maximum, and we get something like this. Okay, so that's, and we'll do one more cycle too. So what's happening to the magnetic flux through this thing? We learned from Lenz's law that when the flux is increasing, the magnetic field produced by the solenoid, this is, by the way, I should say, this is the current as a function of time. What's happening to the current flowing through the solenoid here, okay? So the magnetic flux between this point and this point here, what is happening to the magnetic flux through the solenoid if the current is increasing? Sorry, the magnetic flux through the ring. What's happening to the magnetic flux through the ring between here and here? It's increasing, right? Yeah. So what does that mean about the magnetic field set up inside the ring? Increasing. Magnetic flux through the ring is increasing. What does that mean about the magnetic field inside the ring, though? What direction is it pointing? So, for example, if at some point in time the magnetic field of the solenoid is going this way, and the flux is increasing, what's the magnetic field through the ring going to look like? Same direction or opposite direction? Down. Yeah. Okay. So for the first part, that's what B ring looks like, right? Opposite. Yeah? All right. And the other thing to think about here is basically, for what we're going to do here, just because this will get a little more complicated in a second, the flux through the ring, the time rate of change of that, right, multiplied by a negative sign is equal to the EMF induced in the ring, right? So you're taking the time derivative of the flux, and the flux comes from B, which contains I. So the way I want you to think about this is that if I wanted to plot a function for the current in the ring, then it's always going to be the negative derivative of this, right? So the derivative of this would be like a cosine function, right? But it would be a negative cosine function. So it would start down here, and it would kind of go up like this. Oh, that's awful. It would kind of go up like this. And then it would reach a maximum here, and so on and so forth, right? Okay, so we said between this point and this point that the flux was increasing. What about between, and maybe I can label some things here, maybe we call this point A, point B, point C. Between points B and C, what's happening to the flux now? Oh no, everything's attached. It's decreasing. So what direction is the magnetic field in the upper ring then, if the flux through the ring is decreasing? Up or down? No, not down. If the flux decreases, according to Faraday's law, the induced magnetic field has to point in the same direction as the external field, right? So from, So from B to C, that's what the magnetic field in the ring looks like. It's up. From A to B, it was down, right? Does that make sense? What should happen to this upper ring now? Should it be attracted or repelled from the bottom solenoid between B and C? We need to go to 0 right there, don't we? I'm sorry, did that question make any sense? I know this is really tricky. So, between A and B, do we agree that the ring should be repelled? I'm gonna use a different color here. Between A and B, do you agree that the way I'm graphing it seems confusing? I'm sure it does, yeah. I'm just trying to plot the induced current, because the induced current is related to the induced EMF. The induced EMF is going to be the negative of the derivative of it. So the derivative of a sine curve would be a cosine curve, right? So I would argue that the current flowing through the ring as a function of time should be some kind of like I max through the ring times cosine of omega t, same omega, and then a negative sign. It's negative cosine, Ash. It's negative cosine, right? So it's negative 1 at theta equal to 0, right? Okay. So what I would argue is that between points A and B, the magnetic field points opposite, right? Opposite, which explains levitation, right? This part, levitation makes sense, right? Let's say it levitates. But between B, C, and really all the way down, in fact, let's move C, because it's actually lasting longer. The magnetic flux through the upper ring is actually decreasing for a longer period of time, actually. We could put C right here. Between points B and C, the direction of the magnetic field created by the ring now is going to be in the same direction. See, like this upper arrow and the bottom arrow? That's like a magnet that's like north-south, north-south, right? So south is attracted to north, right? Does that make sense? So you end up getting these different regimes in which some of the time the direction of the magnetic field in the ring is such that it makes it levitate or be repelled, and sometimes the direction of the magnetic field in the ring is such that it makes it attracted. So, to put this in simpler terms, that ring is being pushed between A and B, and then it's being pulled between B and C, and then it gets pushed again. It's being pushed and pulled and pushed and pulled. Like a tug-of-war, kind of. Half of the time it's levitating, and half of the time it's attracted. But yet, you saw what happened. If the period was larger, you'd see it going up and down more noticeably. Maybe. Maybe. But you saw what happened. You saw that it basically just stayed there, right? And Nathan even said something. I think it was Nathan. Didn't you say the rate at which the oscillation is so quick, right? Yeah, exactly. The oscillation is really quick. That's definitely part of it. But even if the oscillation is that quick, right? I don't know. Why does it end up staying up as opposed to falling down, you know? Why does it end up staying up instead of falling down? It reaches an equilibrium point. Yeah. It reaches an equilibrium point, so it falls until the forces cancel out. Yeah, maybe something like that, yeah. The equilibrium point is definitely part of it, because you saw that there was a specific height at which it levitated, and that height was directly related to the size of the flux, because you're farther away from the solenoid. Yeah, so... The reality is, there's something else going on here, and we're going to learn about it in, like, 2 chapters or something like that. And the reality is that the diagram I've shown here isn't exactly accurate. You're saying if it's repelled half the time and attracted half the time, so if it were repelled for any more time than being attracted, it would levitate higher, right? I've been lying to you? How have I been lying to you? Oh. No, there's just something I'm leaving out, is all. The fact is that this bottom curve here, it should actually be either shifted to the right or to the left, based on the fact that the ring itself has what's called self-inductions. So the fact that there's an induced current in this ring means that it produces a magnetic field within itself, right? Does that make any sense? The ring, it has a changing flux due to the solenoid, but it also has a changing flux due to itself, actually. I think, hopefully you can understand why that would be. The current in the ring is varying as a function of time, right? And that current thereby produces a magnetic field for the ring. But this magnetic field is also a function of time, right? So it leads to an additional, what we call a back EMF, basically. It produces a back EMF. If that makes any sense. And the effect of that is it's basically going to shift this curve off to the right a little bit by what I said, like a phase angle, right? Remember in phase angle and like when you're dealing with curves, like sine functions and cosine functions means that the function is like shifted a little bit, basically. So they're shifted such that they're exactly out of phase. Well, they're not necessarily exactly out of phase, but they're definitely out of phase with each other by a little bit, basically. They're definitely out of phase with each other a little bit. And we'll learn about that next week when we talk about inductance. It's 7 o'clock. We should try to do maybe one more problem, I think. So that's something we'll come back to, but anyway. Current in the solenoid is also changing its direction. That's correct, yes. The current in the solenoid is changing its direction. Okay, there are 2 or 3 problems over here that I wanted to do. Since we just talked about this, it's actually identical to the generator problem we were going to do, but... Okay, now I opened Steam by accident. All right, we'll probably do this one. Okay, I have to do this, right? I really don't like navigating around this thing. So there's a generator problem. Let's do this one, though. Because I know you guys have a problem that's like this in your homework. This is related to something we did last time. We only have 10 minutes, so we'll just try to get through this relatively quickly. It's not that hard of a problem. Okay, so we have this picture where we have a bar that has a rail riding on top of it. There's electrical contacts made at this point and this point here, so that you have a closed loop right here. In the picture, there's a magnetic field pointing downwards. And what's going to happen is, naturally, due to just gravity, the bar right here is going to slide downwards. And because the bar is going to slide downwards, and there's a magnetic field that exists in this region here, the idea is that the magnetic field is everywhere pointing downwards. Then what's going to happen to the flux through this loop that's created here, the loop made by the gold rail, the silver rail, and then the resistance here? What's going to happen to the flux through that? It's going to increase, yep, because the magnetic flux increases because the area of that loop is going to go up. So, okay. What are the information we have here? We know that the mass of the bar is 0.2 kilograms. We know that the length of the bar from here to here is 1.2 meters. The inclined plane has an angle of 25 degrees. The resistance is a very simple 1 ohm. And there's a uniform magnetic field of half a Tesla directed downwards. With what constant speed v does the bar slide along the rails? That's our goal here. All right, so we're going to do a couple things here. Because the rail is sliding down the ramp like this, and it's doing so at a velocity that's constant. Constant velocity means equilibrium, right? Equilibrium of forces. So that means that we can draw a free body diagram. This rail is going to have a force pointing downwards, which would be its weight. It's going to have a force that's going back up the ramp. So if this is the ramp right here, there's going to be a force going back up the ramp this way. That force is going to be what we call the magnetic force. And then in addition, there's going to be a normal force pointing this way. And then if that angle down there is theta, then what we'll do is we'll extend this way, and say that if this angle is theta, that this angle is theta, and that'll allow us to break up the weight into components like we normally do in problems like this. Where this is going to be mg times the sine of theta, and this is going to be mg times the cosine of theta. That magnetic force on this rod right here is going to be equal to, now I know it has to point this way, because if it pointed downwards, well, we'd see a problem. The idea is that the magnetic flux is increasing downwards here, which means that the current flowing on our coil has to go this way. You can use Linz's law to find that out. The induced current in the coil is going to go that way, and then this way. Basically opposing the existing magnetic field. And then if the current flows that way and the magnetic field's down, you can use your right-hand rule for this force. FB is equal to IL cross B. That's going to be our magnetic force, and if you use the right-hand rule, a current flowing that way to the right, if you do your right-hand rule, you'll see that it produces a force that goes basically back up the ramp this way, a magnetic force, opposing the weight of the object. Using Newton's second law, the net force in the x direction, let's call this the x direction, let's call this the y direction, should be equal to 0. That means that FB has to be equal to mg times the sine of theta. And then in the y direction, we can say net force in the y direction is equal to 0. That means that the normal force has to be equal to mg cosine theta. And in order to find the velocity, what we're going to now have to figure out is what the current is here. What is the induced current? So we know that we're going to have, in this equation here, ILB is going to be equal to mg times the sine of theta, but we need to know what I is. Okay. So to find the induced current, we're going to use Faraday's law, which says that the magnitude of the induced current is going to be equal to the induced EMF over R, which is going to be equal to negative d times the time rate of change of the flux. And in this case, what I would say is that our flux is going to be B times A. Now, we kind of need a picture here to see this. Maybe you can see it on the picture itself here. If the magnetic field... Here, let's draw this down here. If the magnetic field is pointing straight down like this, the normal vector, or the loop, is going to have an area vector, and I would argue that area vector is going to point like this. Okay, so that the angle between B and A is going to be this angle, which is 90, plus this angle here, which is 90 minus theta. Now, this angle wasn't theta. This angle is like another angle that we could call phi. We'll call it phi right here. And that angle phi is 90 minus theta. So the total angle right here, let's call it theta prime, between the two of them, when we're doing our cosine, we'll do theta prime right here, is equal to phi plus 90. And phi is 90 minus theta plus 90. So it's going to be 180 minus theta. So that would be equal to, since theta was 25, 180 minus that would be 155? Okay. So in doing this then, what we end up getting is, we look at this here and we say the only thing that's changing is the area right here. And so we say that we pull out the cosine of the angle, we pull out the magnetic field, and we just have the time rate of change. I kind of got rid of the minus sign here now that I think about this, because I put absolute value signs in here. That's all we're going to care about. ddt of the area, but the area of our loop, I'm going to say, if we define the x direction to be this way as we did, then the x coordinate of the loop at a moment in time we can just call x, and then our area would be this side x times this side, which we can see down here is L. So you get x times L, but then the L comes out, and what you end up getting is b times the cosine of theta prime times L, and then dx dt, which is going to be the velocity. So you get BLV times the cosine of theta prime. And the problems we did yesterday, you just got BLV because the magnetic field was pointing perpendicular to the loop. Okay, so there's our induced current, and we basically just need to put that right up into that equation right there. All right. So plugging everything back in, we'll have induced current. I is BLV cosine of theta prime. We multiply that by L, and then times B, so we get the L and the B together again here. And then that's equal to mg times the sine of theta. The other thing I would say is that if you take the cosine of 180 minus theta, I'm pretty sure cosine of theta is equal to cosine of... These are equal to each other here because the cosine of 155 is the same thing as the cosine of 25. So we can just write this then as, let's see, scroll down a little bit here. We're looking for velocity. So if we solve for the velocity, that's going to be equal to, let's see, mg sine theta over cosine theta will give us an mg times tan theta. And then we need to divide by b squared L squared. And that'll give us our answer. So we can plug the numbers in there. Anyone have any questions? If you have any questions, feel free to ask. So 0.2 kilograms. Okay, let's move this down some so we can just copy the numbers out of it. So it's 0.2, 9.8, tangent of 25, divided by b squared, which is 0.5 squared, and then times 1. Oh, did I leave out? There's one thing I left out here. The induced current needs to be divided by R. So all of these terms should have had 1 over R, 1 over R, 1 over R. That should have shown up in this equation right here, divided by R. So then the R would show up in the numerator up here, but R is equal to 1 ohm. So it doesn't actually change much for the answer. Now let's see, what was L equal to? 1.2 meters. And you can use that to calculate. I think that's pretty easy to solve at that point. So I'm going to go ahead and stop the recording there. And